All right, welcome to The Explainer. Today we're pulling back the curtain on one of the most important tools in modern software, Docker. We're going to get past all the hype, all the jargon, and deconstruct the so-called magic to show you exactly how a container is built, right from the Linux kernel up.
Okay, let's kick things off with a phrase that every single developer knows and probably dreads. It works on my machine. Oh man, we've all been there, right? Your app runs perfectly on your laptop, but the second it hits testing or production, it just breaks. Why? It's always because of these tiny, infuriating differences in the environment. And this is the exact problem containers were born to solve. So how do they actually solve this? Well, the best way to think about it is with an analogy. Picture a virtual machine as a whole house. It's got its own foundation, its own plumbing, its own electrical grid, everything. It's totally self-contained, but man, is it heavy and slow to build. Now a container, that's more like an apartment. It's got its own walls, its own front door, its own utility meter for sure, but it shares the building's core stuff, the foundation, the main water lines. And that makes it so much lighter and way, way more efficient. And you can see on this slide just how big of a deal that difference is. A VM, it's doing hardware-level virtualization, running its own entire kernel. That's why it's so heavy and takes forever to start up. A container, though, it's just sharing the host's kernel. It's basically just a souped-up, isolated process. And look at the results. Startup time goes from minutes down to milliseconds. The storage footprint shrinks from gigabytes to megabytes. I mean, that is a massive leap in efficiency.
Okay, but wait a second. This brings up a really important question. If a container is just a process, and it's sharing the host kernel, then what is it really? Where does that feeling of being in your own little box actually come from?
And here is the big secret, the thing that blows a lot of people's minds. The term container, it's kinda an illusion. Yeah, really. If you could crack open the Linux kernel and look inside, you wouldn't find any object, any thing called a container. It's not a real object. It's a concept, a clever trick that's pieced together using a bunch of separate, powerful kernel features. Okay, so let's pull this illusion apart and see how it's made. We're going to look at the features that build the walls, the rules that manage the resources, the engine that puts it all together, and then how it all delivers on that big promise of it just works everywhere. All right, first things first, we have to build the walls of our apartment. And in the world of Linux, we do that with a fantastic feature called namespaces. Their job is pretty simple, but incredibly powerful. They control what a process is allowed to see. So the first and maybe most important one is the PID namespace. PID stands for Process ID. What this does is give a container its own totally private list of processes. So inside the container, your app can be process ID number 1, the boss, the init process. And it has no idea that out on the host machine, it's actually, PID 12,345. It literally thinks it's the king of its own little castle. So what does that mean in practice? It means when you run a command like psaox inside a container to see what's running, you only see the processes inside that container's little world. That's it. And that's the whole point. It's what stops one container from messing with or even seeing the processes in another container or on the host itself. Total isolation. Okay, next up, the network namespace. This gives every container its own completely separate network stack. Think of it like every apartment getting its own unique IP address, its own routing tables, its own virtual network card. This is the magic that lets you run, say, 20 different web servers on the very same computer, all listening on port 80, inside their little container bubbles with zero conflicts. It's awesome. And then there's the mount namespace, and this is where the power of this whole thing really hits home. It gives the container its own private file system. This is the secret sauce that lets you do something incredible, like run a container based on, say, Alpine Linux on a host machine that's running Ubuntu. The application inside the container only ever sees the Alpine files. It's completely blind to the Ubuntu host underneath, and that's what gives it that unbelievable portability. Okay, so our container has its walls up, it's living in its own little world, can't see anything outside, but what's to stop it from being a terrible neighbor? Cranking up the music and using up all the electricity and water for the whole building?
Well, that's where control groups, or C groups, come in. If namespaces define what a process can see, C groups define what a process can use. They're like the utility meter and the building rules all rolled into one. They let you put hard limits on resources like CPU and memory, you can prioritize the important stuff, and you can keep track of exactly what's being used.
So for instance, with a C group, you can tell the kernel, hey, this container right here, it can have exactly 512 megabytes of RAM, not a byte more.
And if the app inside tries to go over that limit, the kernel's out-of-memory killer just steps right in, shuts that process down, and protects the stability of the whole system. It's a critical safety net.
So, we've got these amazing low-level building blocks from the kernel itself, namespaces for the walls and C groups for the rules. But how do you actually put them all together to make a container that works? I mean, who's the general contractor here? Well, that's where the Docker engine comes into play. You know, when you type that simple little command, docker run, you're actually kicking off a surprisingly sophisticated chain of events. Your command line client talks to the Docker daemon, which is called Docker deed, but here's the cool part. The daemon doesn't actually run the container itself. Nope, it hands off the request to another piece called container deed, which is responsible for the container's lifecycle. And then, container deed uses a really low-level tool called run to do the final step, talking to the kernel to actually create the namespaces and C groups. It's this beautiful, clean separation of jobs.
But Docker's real genius isn't just in how it wrangles these kernel features. One of its most game-changing ideas is how it handles storage. See, unlike a VM with its one giant monolithic disk file, Docker images are built in layers. It's a completely different approach.
And this system uses a brilliant strategy called copy on write. All those base image layers, they're read-only. They can't be changed. When you start a container, Docker just slaps a thin, writable layer right on top. So if your app needs to read a file, it just pulls it from one of the shared base layers. Super fast. But the moment your app tries to change a file, the system instantly copies that file up to the top writable layer, and the change is saved there. This is why starting a container is almost instantaneous, and it's how you can have hundreds of containers all sharing the same base image without wasting a ton of disk space. It's just so efficient.
And so, all of this amazing tech, the namespaces, the C groups, this brilliant layered file system, it all comes together to finally solve that maddening works on my machine problem we started with.
The answer is a powerful idea called immutable infrastructure. A Docker image? It's not just your code. It's a sealed, unchangeable package. It's got the operating system files, every single library, all the configuration, and your code, all bundled up together. This one, single, versioned artifact becomes the thing you deploy. And that right there is the huge mental shift. You're not just shipping your code anymore and kind of crossing your fingers that the server is set up right. No way. Instead, the machine itself, that entire perfectly configured environment, is packaged up and travels with your code. From your laptop to testing to production, the works on my machine problem is gone because your machine is now everywhere. So, let's wrap this up. The biggest thing to remember is that containers aren't some black box magic. They're just a really clever combination of standard Linux kernel features. You've got namespaces to provide the isolation, controlling what a container sees. You've got C groups to provide the limits, controlling what it can use. And you've got Docker images and that layered file system to give you that incredible portability.
But here's the thing. Everything we've talked about today, it's all been about managing one container on one machine. We've figured out how to make the perfect brick. But what happens when you need to build a skyscraper, a massive, resilient system with thousands of these bricks spread across a whole fleet of servers? What happens if a server dies? How do you automatically move those containers somewhere else? How do you scale up and down? Well, that's where orchestration comes in. And that leads us to the final thought. If containers are the bricks, you need an architect like Kubernetes to actually build the skyscraper.